Very good morning, my dear friends. Myself, Professor M.H. Annaya, and in today's video, we are going to learn about an eccentrically loaded welded joint. So, eccentrically loaded welded joint indicates that the load is not acting through the center of gravity. So, friends, in today's video, we have a horizontal plate welded to a steel column by means of an L-shaped welding. This is L-shaped welding and the dimensions are given to us. So we are required to find out what is the size of the weld required to sustain a load of 20 kilonewton. So this is the question for today's video. Friends, basically what happens when you want to find out the size of the weld required, we have to first of all identify at which point in the welding the maximum load is acting, or which point in the welding done the welding is critically loaded. So that is to say, there are two ends. One is A, other is B. There are two ends. We have to identify in a welded joint which is the point where the maximum load is acting. So it could be A or it could be B. And it has been found out by practice that for such a welded joint, the point which is farthest from the center of gravity, CG, will be heavily loaded or critically loaded. And friends, very obviously, we have to identify and find out what is this G and what is the distance of that G from that point where it is critically loaded. So as per the diagram I have written, the point B, which is farther compared to that of point A, is critically loaded. So you will have to find out the at the point B, what are the loads acting, what type of loads are acting, and what is the resultant load. And based on that resultant load, we are going to find out the size of the weld. So friends, let us start or commence the problem by finding out the center of gravity of the weld. So step number 1, I find out what is CG of weld. CG of weld indicates that is X bar comma Y bar. So this is the first step. And along with this, you will also find out what is E, the eccentricity. Eccentricity stands for the distance between the load line and the CG. This distance is called eccentricity, and I have already marked on the diagram. You can see what eccentricity is. Friends, if you observe this welding, the L-type welding we have got here, this is not symmetrical either about the horizontal axis or about the vertical axis, and hence we need to find out both X bar and Y bar with reference to some reference line. Say this is the Y axis, say, and this is the X axis. We'll have to find out at what distance from the X axis and distance from the Y axis the CG lies. And friends, here, if you refer to the design data handbook, that is machine design data handbook, in the machine design data handbook, for a giant like this, they have indicated G distance as Cy and Cx. Cy is nothing but X bar, and Cy is given by the formula, Cy is given by the formula B square divided by twice B plus D. And similarly, Cx is given by the formula D squared divided by twice B plus D. So what are these B and D? Friends, in this welded joint, B stands for the width of the weld and D span for the depth of the weld. So as per the diagram, B is equal to 100. I'll write down here B is equal to 100 and D is equal to 150. And if you substitute, friends, you will be able to get the value of Cy as 20, that is 20 mm. And similarly, friends, the value of Cx works out to 45 millimeter. It's a simple substitution. You will get the value. That is to say, this Cy is x bar and this Cx is y bar with reference to this. Friends, we have found out what is Cx and Cy, and now I have to find out E. E stands for the eccentricity. Friends, if you observe this figure, from the load axis to the CG, center of gravity is E. We know this distance. So, from the total distance 250 plus 100, that is 350. If you subtract Cy, you will get what is called eccentricity. So, I will write down here E is equal to the total distance, that is 250 plus 100 is the total distance, that is from the load line to the end, minus Cy. This is 350 minus Cy is 20, that is 330 millimeter is the value of eccentricity. So we have completed the first part of the question, that is finding out the CG and the eccentricity. Friends, let's move on to the second step, step number 2. In step number 2, friends, we are going to find out the direct load, that is to find direct load. Friends, direct load I have designated as PD. Direct load is PD, and this PD is given by the formula P divided by the total length of weld. Total length of weld. So this is applicable for all such case of eccentrically loaded welded joints. What is P here, friends? P is the load, that is 20 kilonewton, and that will always be given to you in question. That is 20 times 10 to the power of 3 Newton is the conversion from kilonewton to Newton. And friends, this total length of weld, if you observe the figure, the total length is the width plus the depth, that is B plus D. Total length of weld is equal to B plus D. B is 100, depth is 150, so you are going to get 250 millimeter as the length of weld. And if you substitute in the formula, you will get this PD equal to 20 into 10 to the power of 3 divided by this 250. Friends, this works out to 80 Newton, that is 80 Newton per millimeter, because the load is in Newton and the length is in millimeter. Hence the units are 80 Newton per millimeter. So we have got the value of the direct load as 80 Newton per millimeter. And now comes the question, where does this load act in the weld? I told you in the beginning of this video that this load, both direct and the secondary load, acts at the farthest end of the weld. So from GA, the end A is nearer compared to this B. So very obviously this direct load will act here. I will show you a separate diagram later on. This is our direct load. So we can make a comment here that the direct load PD acts at B, the farthest end of the weld, and its value is 80 Newton per millimeter. And how does this act? Friends, this PD acts parallel to this applied load capital P and in the direction of it. So this PD is parallel to P. P is acting downwards, so also PD is acting downward. This is applicable again for all types of eccentrically loaded welded joints and also riveted joints. Friends, we have marked the direct load. Its location also has been identified. And in step number 3, we have to find out what is the secondary load. What is the secondary load? That we call it as PS, secondary load. Friend, this secondary load PS arises on account of the eccentricity. So because the load is not is passing through G, it is passing at a distance, and this causes a bending moment, and a secondary load has to be found out before we arrive at the resultant load. Friends, this PS is given by the formula PER by J. This is available in MDH. In the machine design handbook, you find this. So friends, P stands for the load, that is 20 into 10 to the power of 3 Newton, and the eccentricity we have found out already, that is 350 minus Cy. 350 minus Cy, that is 330. We have done this calculation in the very first step. Then comes R. What is R here, friends? R is the distance from CG to this point B, the critically loaded point. So how to find out this? In this right angle triangle, this value Cy is known to you, and this is Cx. So if you know what is the value of Cy and what is this height, you'll be able to get that value. So friends, so here we can say R is equal to this square plus this square. Cy square plus this distance is 150 minus Cx. 150 minus Cx square under root, because it is a right angle triangle. Friends, if you simplify this R value works out to 106.89 millimeter is a rate distance, so it is millimeter. Next, we'll find out what is JW. So friends, JW is the polar moment of inertia for this type of joint, and you refer to handbook, you'll be able to get its value, and this is given by B plus D to the power of 4 minus 6B square D square divided by 12 times B plus D. 12 times B plus D. This is the equation. Friends, you know B is equal to 100 mm, D is equal to 150 mm. Substitute the value in this and you will get the value of J. W or simply J is equal to a value 852088 852088.3 mm cube. This is the polar moment of inertia. Friends, we know all the values, that is of P, E, R and J. And if you substitute these values in the secondary load formula, that is P, E, R by J, you will get this secondary load as 827.94 is again Newton per millimeter. Friends, like our direct load, we have calculated the secondary load, and we will have to see how this secondary load acts at the critically loaded point in the weld. The critically loaded point in the weld is B, the direct load is acting here, and this secondary load will act at the same point, and it will be acting perpendicular to R so as to produce a moment similar to the moment produced by P about CG. In other words, P is producing a clockwise moment about G. So also the secondary load acting here, the secondary load PS acting here, which is perpendicular to R, should produce a clockwise moment. So this is producing a clockwise moment. This is how this PS acts, friends. Now friends, we have the direct load, we have the secondary load, and you will have to find out what is the resultant of these two before you find out the thickness of the weld required. Friends, we have this formula. The resultant load is square root of P direct square plus P secondary square plus 2 times PD PS into cos theta. That is, if you have got two forces, PD and PS acting at an angle theta, the angle between these two is theta, this is PD and this is PS, and the diagonal of this will give you the resultant load. This is a high school problem you have probably studied in high school. So the resultant of these two is given by this formula. Friends, we know these values. PD we know, PS we know. Only that cos theta, that theta we have to find out. What is that theta? Friends, if you refer to this figure here, the angle between these two, this angle is theta, and the resultant whatever we are getting here, the resultant is resultant of these two. So I will say this is the resultant, which is called PR of PD and PS. So this angle theta I will have to find out. So calculation of this theta from that point B is very important. So I am going to write down separately these values. So friends, this is our PD, and we have this R here, the radius is R, and we have this secondary load perpendicular to that R. So this is what the point B I am showing you, friends. At the point B, we have the direct load, we have the secondary load PS, and the angle between these two is called theta, and the resultant of this is represented by the diagonal of this parallelogram. This is our PR. Friends, remember, without knowing the value of this theta, you cannot find out PR and hence the size of the weld. So these geometrical relations are very important. Friends, here you can just see this is CG somewhere here, and we have this R. This is acting perpendicular to that. Friends, here, whatever the angle you get here, is same as this angle. So this angle, if I call it as alpha, this is also alpha, and the value of theta we need is this alpha plus 90 degree, because this is 90 plus alpha will give you theta, the angle included between PS and PD. Friends, how to find out this alpha is the next question. If we come back to this diagram, friend, so this is our opposite side and this is the adjacent side. This is the hypotenuse of this right angle triangle. We want cos theta in the formula. So we will directly write down what is cos theta. Cos theta is equal to the adjacent side. Adjacent side is 150 minus Cx. 150 minus Cx divided by the hypotenuse is r. Friends, we know 150 the value. Cx value is 45 millimeter and the value of this radius r we have found out already, that is 106.89. 106.89. So you will get this value of cos theta directly. And friends, this theta works out as 100.76. So if you want this cos theta, and we have got this theta is equal to 106.78. 106.78 degrees. Friends, this part of this calculation is very, very important, because if you go wrong in the calculation of theta, you get a wrong value for the thickness of the weld required. I hope, friends, you're all following it clearly. Now, friends, let us move on to the last part, that is the final part of the question, that is say step number 5. That is, we are going to find the size of weld. Size of weld, we call it as H. So, friends, after knowing PD, PS, you can find out that PR, and this PR value works out to 846.77. 846.77 Newton per mm is the value of PR. So we are going to equate the shear stress tau to PR divided by 0.707 H, where tau is the shear stress for the weld material, that is given as 75. That is PR we have calculated 846.77 divided by 0.707 into H, an unknown. So friends, this H works out to 15.96 mm, and we can approximate as H is equal to 16 mm, a round figure. So hence, for this eccentrically loaded welded joint, we need the thickness of the weld as 16 millimeter. Friends, finally I hope the presentation was interesting, and after going through my video completely, if you find this is interesting and of benefit to the students of engineering, do subscribe to my channel, give a liking to it, and share this information with all your friends. Wish you a nice day.